record. We are on a new unit, Unit 6, which is Newton's laws. All right, so something tells me by your groans that you've experienced Newton's laws before. So you want to throw some at me? Object in motion stays in motion, okay. We're just throwing stuff out, it's okay if it's not perfect.
I thought we did this.
There's an action-reaction one. What else? There's a what?
The butterfly effect.
I don't know what the butterfly effect is.
That's not.
Okay, so we had object in motion stays in motion. That's basically like Newton's first law. The action-reaction one, that's basically Newton's third law. And then what else? No, that's the first one, the rest one. What is Newton's second law? That's maybe it's more complicated. It's the one that relates acceleration, net force, and mass. Maybe you didn't do them actually. I don't know.
They're somewhere in my engineering notebook from 7th grade.
Okay, no, and that's okay if you don't know it. If you don't know it yet, because that's literally why we're here. Okay, so last unit we described motion. How did we describe it? What did we use to describe it?
Average speed.
Right, we talked about speed. What else? Speed, velocity, yeah. What else? Okay.
Question mark?
What?
Time?
Okay, we did talk about time. Acceleration. What's the other one, guys?
Displacement?
Yeah, or position, right? So basically we said, hey, I see an object moving. And I could say, hey, where is it? How fast is it going? How fast is that speed changing? Right? How much time does it take to get from one place to another, right? These are ways that we've described motion. But we didn't tell you why any of that happened, right? So now, this unit is why.
What's up with the screw?
That's sad. Okay, 4 different situations. 1, need a pen. What? 1. A book sitting on a desk. Not to, but that's fine. Okay, so the book is sitting on the desk. You said it had 0 acceleration. Okay. Okay, it's not going anywhere. Interesting. So you see it has no acceleration, no, right? No delta x, right? No displacement means it's not, right, going anywhere. Oh my goodness, what was that in the hallway? Okay, it's not going anywhere. My gosh, that says anywhere. You'll have to trust me on that. Okay.
Any shoe.
What's that?
Looks like any shoe.
Sure. But we'll just assume that it says anywhere.
Yeah.
Okay, you might also say something like, it's not moving. Right? These are all appropriate things to say. All right? How about number 2? I'm going to drop a ball. Are you ready? Oh, it's exciting. Ah! Oh, I said I was going to drop it. I didn't say I was going to catch it. Okay? So, drop a ball. What do you think?
Is that a golf ball?
There is displacement. Okay? So, there's displacement. Okay, what else?
Velocity is increasing.
Ooh, you said velocity
Then it changes.
is increasing. Okay. What other words can we use to describe this?
Acceleration.
It's accelerating. Okay.
Didn't you say the velocity changes when it comes back up?
Yeah, when it hits the ground, that's a whole nother thing. Then it actually slows, like as it goes down, it's speeding up, hits the ground, then it starts actually slowing. It turns around, it slows down, then it hits the top, and then speeds up again. There's lots of different velocities going on, right? The velocity is changing, okay? All right, here we go. I'm gonna roll a bowling ball. Rolls across the floor. Okay, I'm gonna pause this. So what did you see about the bowling ball?
There was friction.
You saw that there was friction.
Yes.
How did you see that there was friction?
Because it slowed down.
Did it slow down?
I don't know. I was just trying to.
Okay.
I guess we should not.
It was moving.
It was moving,
Constant velocity.
and
No, I also don't pay attention.
did you see that that bowling ball was basically constant velocity? Okay, right? Bowling balls are pretty darn good at, like, once you let go of them, they stay that speed for a really long time. Okay? What other words could I use to describe that? No acceleration? Cool. Cool. All right, let's do one last one. And I'm going to push a book.
Dropping in the end.
I know, push a book. It's so boring. Ooh, you said friction. You said friction slowed it down. So it slowed down. And you know that friction slowed it down. Why? Because it slowed down, and you've had other science classes before where they told you about friction.
Exactly.
Interesting. So you're coming in here having some understanding of friction. That'll be important in a little bit. So, slowed it down. If something is slowing down, what else can we say?
It's
Changing velocity.
Ooh, okay. So changing velocity. What else?
it decelerated.
So we're gonna actually still call that acceleration. The word deceleration, which generally is a normal English word meaning slowing down, okay? That's not a physics word. It just means that the acceleration is in the opposite direction of the velocity.
So negative.
Yeah. So remember on your test and everything and all the things we've done where you did things where they slowed down and you calculated the acceleration and you got a negative acceleration, right? So again, the word deceleration is not a physics word. That's an English word. But we just say that's accelerating. Okay. Cool. So now my question is, can I go to the next slide? Are you guys
No.
just kidding? All right, so let's look at these 4 situations and see if we can come up with anything. So why is the book just sitting there in number 1? Why is the book just sitting there? Victoria?
There's no outer force acting upon it.
Okay. You say, I'm going to say no external. Is that the word you're
Yeah.
looking for? Forces. Okay, that's one way to put it. Are there any forces on it?
Yes.
What are
Besides
they?
gravity.
Right.
Okay. So, like, you've got the weight. What else?
It's at net zero though.
Okay. What else is happening to this book?
Nothing.
Yeah, August?
Gravity.
Gravity. Okay, got it. This is gravity. Anything else? Is this book experiencing anything else, Victoria?
Well, gravity is trying to pull down on it, but since it's on a solid supported surface, it can't go any further because,
Okay, so you're saying there's something about this table.
yeah,
Is the table
Pushing back.
pushing on it?
no.
Yes.
Yeah? Wait, things?
Yes.
Yeah. Which way? The table's pushing up. Good job.
Huh.
If it wasn't pushing that, it would have been
Because if it wasn't on the table, where would it go?
on the floor.
It would go down like the ball, right? So the ball here, right, has its weight. But that's it. Sorry. Gravity, weight, same thing, guys, right? The force due to gravity is weight. Can I get some vigorous nods on that one? Okay. All right, what about our bowling ball?
Inertia?
That's an interesting word.
I learned it from Bill Nye the Science Guy.
What's that?
I learned inertia from Bill Nye.
Good. We're going to talk about inertia today.
I did not like I'm gravity.
Okay, you know what? Let's leave number 3 for a second. Let's talk about number 4. I pushed the book. And what happened? It slowed down. Why?
Because of friction.
Friction. And which way was friction pointing?
Left.
Yeah, this was friction. Okay. Let's go back to this bowling ball.
Friction was going the other way.
Friction's actually really complicated when it comes to rolling. We're going to ignore friction for a second. Yeah?
If the friction was the exact same as the acceleration, then it would be stopped. Therefore,
So you can't really equate friction and acceleration because friction's a force and acceleration's an acceleration. So we can't really say that. We're going to ignore friction for right now for the bowling ball. I want you to just imagine it's just going nicely, constant velocity. Okay?
should we put that down?
Well, yeah, I will in a second. But what forces are on this?
Gravity.
Okay? Right? So it's weight, which is gravity, and what else?
External.
The floor, right? Okay. Have you guys ever heard the phrases balanced and unbalanced forces? What does it mean? August?
Basically means if the forces are balanced, nothing happens, but if the forces are unbalanced, something happens.
Okay. And if we think about literally what a balance looks like, right? Got one arm over here, one over here, right? If they're balanced, right, this is equal to that, right? But if it's unbalanced, so this guy's not getting pulled or whatever, someone pulls me this way, right, that's unbalanced. So I think everybody has like an idea about balanced versus unbalanced, right? So with these 4 situations, can you tell me if they're balanced or unbalanced? One is what?
One is balanced and the other is
Okay. So 1 is balanced. 2, would everybody agree, is unbalanced? It's only weight and also here. Okay. This, don't close it all the way. Okay. Number 3, what's the difference between number 3 and number 1?
Number 3 is moving.
Number 3 is moving, but look at the diagram for the forces. They're the same. So guys, check it. This is balanced forces. What can we conclude from this? Aiden.
Rolling is a balanced force.
Okay. But do you see that? Okay, so over here is balanced. Over here was unbalanced. Can you tell me what these things were doing? August?
Accelerating.
Yes. Both of these. Oh my goodness. That's some good.
Yes.
Okay. Accelerating. And what about these guys over on the left? Yes, Victoria.
slowing down.
Number 1 and number 3, we're not slowing down.
What? Oh, sorry.
Number 1 and number 3,
They're staying the same speed.
yes, not accelerating. Not accelerating. And you said staying the same speed. We're going to be a little bit more specific about that.
Same velocity.
Okay. What's that? Same velocity, yes. And we're going to write that in a second. But do you see with these 4 different situations that when we have unbalanced forces, and I'm going to write this on my next slide because it's so important. Unbalanced forces means that the object changes It's velocity. And when you have balanced forces, it does not change velocity. What do you think about those two statements? Are we feeling all right about it? Okay. Have I told you anything new? What have I just said that's new? Because I know that you've talked a lot about this before, but maybe haven't used some of the same words. So can you tell me what's a little different? Or is everything clear? Like you've talked about forces, unbalanced forces, balanced, that stuff? Okay. So, by the way, hold on, I didn't mean to do that. Change velocity is telling you what? Yes?
Accelerate.
Okay, that's leading you to acceleration. Okay, so we're going to try to make sure that we use that word. Now, I'll remind you that velocity is both, okay, I'm bored of black, I'm going to change. Velocity has speed and direction, right? So, to change velocity means what?
Change speed and or direction.
Exactly. To change speed and or direction. Okay. So the other part of this, so Gwen, are you not taking notes today? Okay. So to change speed and or direction, but here's the really important part. So important that I'm going to change colors again. Okay?
Green.
Sorry. What does it mean to have no change in velocity? Yeah?
It's moving at a constant speed.
Very good. Constant speed in a straight line is how I'm going to write it. So when you think about constant velocity, I want you to think about that bowling ball. That bowling ball is a really, really good approximation of constant velocity. Okay? It is going in a straight line at a constant speed. Okay? I see that you're trying to catch up with notes. All right, we have Newton's first law. And what is this law? Do we have a feeling for what it is? Like just because you've learned it before? Yeah, Gwen.
Every action has an equal and opposite reaction.
No, that's a third law. But
How many are there?
there's three. Well, there's 3 laws of motion. Newton had a lot of laws, but we're going to focus on these 3 laws right now. So it has to do with what we're talking about. Yes.
Objects in motion stay.
Okay. So I'm going to write it pretty specifically. Okay? An object at rest stays at rest, and an object in motion, and you might want to say like stays in motion, but I want to be a little bit more specific. Stays at a constant speed in a straight line. Unless, I know this is a lot of words. I'll pause after I finish writing it. Unless acted upon by an unbalanced force. So I'm going to pause to let you write, and then we're going to talk a little bit more. When we look at this, we see at rest, and we see constant speed in a straight line. What is another way of saying that? Yep?
Forces are balanced.
The forces are balanced, okay. And so actually, I want specifically, when we say that something's at rest or a constant speed in a straight line, talk to me about we're not talking about forces right now, we're talking about how we would describe its motion. Like last unit. What's that? Constant velocity. And also, what? Acceleration is 0. Okay, so that's what we're talking about. So you can boil this down to objects will have no acceleration unless there's an unbalanced force. Okay? And I don't like that I put that in red. I'm taking that away. Okay. How's that feel? It's all right?
Yep.
Awesome. So what does it really mean? What this means is that things want to keep doing what they are doing. And this might seem easy. However, I want you to think back to when you learned about friction. Do you guys know when you learned about friction? No, you don't, do you? Well, you've probably heard the word friction your whole life, right? That's just a normal idea. Our life has friction in it, right? That is what you are used to seeing, okay? So this is why Galileo was so dang cool, because he imagined a world without friction, which is really hard to do because it's all around you. Because when you see things, everything that you see in your daily life probably comes to a stop. Think about it. Right? We did that bowling ball, that was great, but it was going to eventually come to a stop, right? So everything at some point comes to a stop. That's your daily life. But Galileo was like, what if there was no friction? Then what would things do? And what he realized, right, was that things actually want to just keep doing what they're doing. And the only reason that they change any of that is because of forces. And that's a big deal. Okay? Just that idea is a big deal. All right? He actually did this. I'm going to pause this so I can go do a little demo. All right. So they want to keep doing what they're doing. And there is a word for this. Okay? And that word is inertia, which some of you mentioned before. And inertia is the property of an object to resist a change in motion. And now we're going to do like 12,000 demos. Okay? But let's just wrap our brain around this word, inertia. This is an English word. Have you ever heard this word before?
Yes.
What does it mean? It means that, right? Yeah, Malachi's like, duh, you just wrote it down. Now, in this case, inertia is very, very similar English and physics meaning. In physics, very often we have words that we use in physics that mean something completely different. Remember the word work? Right? Work had a very specific physics meaning. But here, inertia is basically what you think it is. It's something not wanting to change. Okay? And so there's a few great inertia memes that I will show you first. what did the NFL video say about what is a good measure of inertia? Like what causes something to have more inertia? More mass. So mass is a measure of inertia, right? More mass means there's more resistance to change. Does that make sense? So think about an elephant and a mouse. And not a versus, but an elephant and a mouse. Okay, you're standing there and a mouse is running at you, right? Okay, what do? You scream. First, you scream. You have to scream. That's important. You do not step on the mouse.
Yeah, you do. Step
Oh.
on his head.
No. Right? So you could run away, right?
Depends on if it's a pet mouse.
It depends on if it's a pet mouse. Okay. It's possible I've gone off track.
Get the 9.
Okay, let's back up for a second. What about the elephant? The elephant is running at you.
You step on the elephant.
You step on the elephant.
Go dive into
No. Good luck. What can you do,
You go to the
Marin? What can you do?
Well, you would,
I can't wait till
Elijah.
you try to move out of the way because
You,
elephants are bigger than
yes. So elephants have, right, more mass.
therefore they.
And so if it's running this way and you're here, you could kind of like zigzag out of the way, couldn't you? Because it would be really hard for the elephant to change its motion because of its large mass. Does that make sense? Okay. And now it looks like I just like drew like a Harry Potter thing. Okay, that's confusing. Okay. Actually, so we're almost done. I just want to write one more thing. I'm sorry, what? Did you mispronounce yay?
Yay.
Exactly.
Sure. Don't have back on hers, not gonna lie.
Mass.
Be my number.
you squatted over 5 pounds.
Yeah.
So just because we're going to be using it again, I want to make sure that it goes in to your table of friends. What is the variable for mass?
M.
M. And what is the SI unit?
Kilograms.
Kilograms. You got it.
Oh, it's already in there.
It's already in there? Fantastic. Okay? And just remembering that mass is the amount of stuff in an object. That's going to be important as we move on. All right. Okay. Newton's first law, because of all the stuff that we've been saying, is sometimes called the law of inertia. Okay? That's all I wanted to say. There we go.